Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving an equation. I guess we could call this a rational equation, but we're also going to be using Euler's formula. Okay, so a couple different things. We have the quotient of z minus I and z plus I, and that's equal to e to the power I theta. Hopefully this is familiar to you. If not, if you're new to complex numbers, go ahead and check out the lecture videos. So, in order to solve an equation like this, obviously there's a couple different ways we can go about it. Let's go ahead and start with something. So I have z minus I over z plus I equals some other complex number, which was expressed as an exponential, right? So our goal is to solve for z, so we might as well just replace z with something like a plus bi, right? And then if you do that, you're going to get a plus bi minus I divided by a plus bi plus I. Let's go ahead and simplify this a little bit, and then we're going to set it equal to e to the power I theta. Okay? Now, how do you simplify something like this? I can go ahead and put together the imaginary parts like this. And then I can actually go ahead and I should probably write it down here. I could go ahead and just simplify this by using the conjugates. Complex conjugates are very helpful especially for division problems. I can go to multiply this by a minus b plus I. So I just change the imaginary part of the denominator, and then I get that. And here we're basically gonna distribute, right? Real parts by real parts, real by imaginary, so on and so forth. A times a is a squared, and then a times b plus 1i with a negative sign, so it's going to be a minus a b plus 1i, and then same thing but with this time b minus 1, and that's a plus sign, so it's going to go like this. And then finally, when we multiply b minus 1 and b plus 1 from difference of two squares, we're going to get a b squared minus 1 with a negative sign, but I squared is negative 1, so that'll be negated one more time, and we're going to end up with b squared minus 1. Make sense? I hope it does. And then all of that is divided by sum of two squares. Remember, when we multiply by conjugates, we get sum of two squares. Now we can go ahead and simplify this a little bit by putting the real parts together, a squared plus b squared minus 1. And then the imaginary parts are basically going to be like minus ab minus a plus ab minus a. And ab is going to cancel out. We're going to end up with minus 2ai. And that is divided by a squared plus b plus 1 quantity squared, and that's equal to e to the I theta. What are we trying to find here? Are we trying to solve for theta or z? We're trying to solve for z. So I guess we could say that we're trying to solve for z or find z in terms of theta. Okay? Let's see if we can do this. Obviously, to be able to do that, you do need the a value and the b value, right? So you kind of need to be able to write it as a plus bi. So how do you do that? From here, we can basically separate this into two fractions like this, and then we could probably just write it like that, and then don't forget the I, and this is e to the I theta. Again, e to the I theta doesn't make so much sense here because we're comparing something in polar form to standard form. Let's go and write e to the I theta in polar form, or standard form, I should say. So what is e to the I theta by Euler's formula? It's cosine theta plus I sine theta. Great. So let's see how this works. The real part, since these two complex numbers are equal to each other, this is going to equal the real part, which is cosine theta, and this is going to be the imaginary part with the minus sign, of course. That's going to be sine theta. And from here, you basically get the sine theta and the cosine theta, and then hopefully you can solve for a and b, but that's going to be a little painful. You could probably do the following at least. Sine squared plus cosine squared is equal to 1, so you could go ahead and square these, add them up. That should give you something, but that's going to take a long time. So that's not the best way to do it, but I still wanted to show you. And let's proceed with the second approach. Okay? One more time, the problem is z minus I over z plus I equals e to the I theta. Maybe there's an easier way to simplify this. I can't really see a quick method to come up with ab values other than squaring sine and cosine. Now, since we were given a rational equation, why not cross multiply and try to solve for z? Let's do it. By the way, if you multiply as by z minus I, you're going to get z squared plus I squared, which is -1, and that is not going to be real. So the multiplying by conjugates only works if you have a number in the form a plus bi, not z plus I. Okay? Cool. Let's go ahead and cross multiply here. Z minus I is equal to z e to the I theta plus I e to the I theta. Of course, since we're trying to solve for z, let's go ahead and put all the z values on the same side. Z minus z e to the I theta equals I plus, I should probably write the e to the I theta first, e to the I theta plus I. And then if you factor out a z, 1 minus e to the I theta equals I plus e to the I theta. However you want to write, doesn't matter. No big deal. Let's write it this way first. Great. So what do you do with that? You can basically just divide by 1 minus e to the I theta. That's going to give you z equals e to the I theta plus I divided by 1 minus e to the I theta. And at this point, we may want to simplify this a little bit, even though this is fine. This is the z value. Let's go ahead and simplify. Now, again, write what e to the I theta means. So e to the I theta is going to give us, and you could do this in the numerator and the denominator, so like cosine theta plus I sine theta plus I, and then divided by 1 minus cosine theta minus I sine theta. And of course, this can be simplified a little bit, right? We can write this as cosine theta plus 1 plus sine theta all multiplied by I, and then that's divided by 1 minus cosine theta minus I sine theta. Doesn't matter either sine theta I or I sine theta. The problem is at the bottom we could use double angle formulas, but I don't think it's going to work for the numerator unless we make some changes, and that's going to be kind of like time consuming. Let me just quickly show you, because if you replace theta with pi over 2 minus theta or 90 minus theta, you're going to get the following: sine 90 minus theta. I'm going to use degrees since it's a little easier, and it's going to be 1 plus cosine of 90 minus theta. Now, why did I change those? Let me explain why I did that. Because now I can basically replace this one with the double angle formula. And remember, if you treat this as sine 2 alpha, you're supposed to cut this in half, right? So it's going to be half of this. So I'm going to treat this as 2 alpha, and this is going to be 2 alpha. So sine 2 alpha is 2 sine alpha cosine alpha. In other words, 2 sine 45 minus theta over 2 times cosine 45 minus theta over 2. And with the cosine, I can go ahead and use the double angle formula. And the way double angle formula works for cosine is there are actually 4 formulas that you can use. But the one that's going to be good for you is the one that will get rid of the 2 here. So we're going to be replacing it with 2 cosine squared 45 minus theta over 2 minus 1. And of course, that's all of that is multiplied by I. 1 cancels out. And then what you can do is you can basically factor out a 2 cosine 45 minus theta over 2 here. And then that's going to give you sine 45 minus theta over 2 plus cosine 45 minus theta over 2. Again, you can write this as e to the I something again. And at the bottom, we can do something similar, but it's going to be half of theta. These are 45 minus theta over 2. Anyways, I guess we might just leave it as is. This is fine. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.